All right, guys, so we are going to be using the book today, and if you are at home, then this is going to be what you want to log on using. It's http://www.bigideasmath.com/Northside The login username is your S number without the S, so it's just the 6-digit number, and then it's your 4x4. I am on page 210. It's the beginning of chapter 5.1. We're going to be talking about polynomial functions. So right here it just says, recall that any monomial is a number, a variable, or a product of a number and one or more variables with whole number exponents. So, and then it says a polynomial it's a monomial or a sum of monomials. So here's some examples of polynomials right here. These are all polynomials. So it's a monomial. Here's a binomial or a sum of monomials. So you have like 1, 2, 3 monomials added together here. 1, 2, 3 monomials added together here. You can have infinitely many monomials added together and it's still a polynomial. Another thing that's hugely important for something to be a polynomial is, you see this part right here. It says a sub n cannot be 0, so it's saying that, of course, the 5 can't be 0, the 2 can't be 0, the 1 that's in front of this x can't be a 0. You can't have 0 coefficients, that's what it's saying. That's pretty straightforward. But it also says the exponents are all whole numbers. And remember that a whole number is pretty much any number, it's any solid number like 1, 2, 3, 4, or 5 going to infinity. It cannot be negative, it cannot be 0. Okay, so that would be what a whole number is. So your exponents also have to be whole numbers. Something else to keep in mind is if your exponents, this is what it would look like if it's not a whole number. Let me create an example, like 2x to the negative 1 plus x plus 2. All right, so that's not a whole number. That's a negative exponent. Now, here's something interesting. X to the negative 1 can also be written, x to the negative 1 also can be written as 1 over x. So, for example, if you see something, notice I'm going to rewrite now this entire thing. Let me use this pencil. I'm going to rewrite this in a slightly different format. So if I have x to the negative 1 here, I can also write it like 2 over x, because notice the x to the negative 1, it pretty much just drops the x down into the denominator. So if you have fractions, also that's not a polynomial. Plus x plus 2. So that's another example of the same exact equation written a different way. So really what you're looking for that's going to cause something to not be a polynomial is if you have a negative exponent or if you have a fraction. Another thing that you could be looking for potentially is if you have some kind of like decimal as in the exponent. Armando, were you working on this? Were you working on it Friday or not? Yeah.
No, so we covered it on Monday.
Okay, here you go. I got you covered. Sorry guys, just a second. Is that? Yeah. I thought you came in Friday for some reason. Okay, so sorry about that. So another thing that you could be looking for is if you had an exponent that is written like this, x to the 0.5. Or maybe we all know that 0.5 is the same thing as 1/2. So x to the 1/2. And what that actually means is x to the 1/2, surprisingly, is the square root of x. That's also not a polynomial function. If you see something like a fractional exponent in a in your function, then it's not a polynomial function. And then the last thing that we could possibly see is, let me write out one example with this real quick. So that could look like this in an equation. Maybe you have x squared, let's say 2x squared, plus 6x plus x to the 1/2 power plus 6 equals y. Something like that. And you see that 1/2 power right there. That's going to make it not a polynomial function. Last thing you could see is maybe something like x squared plus 2x plus 3 to the x power plus 6. If you have an x in the exponent, that is not a polynomial function, that's an exponential function. If you have an x in the exponent. Okay, so those are examples that would cause something to not be a polynomial function. So when you look at all these are all polynomial functions. The example 1 right here just asks you to determine if a, b, c, and d are polynomial functions. So you look at a, it's got x to the third, x to the first, and it's got a nice whole number right here for your a naught on the end. So that's fine. That is a polynomial function. You look at b, you have x to the third, you have square root of 2, that's fine. If it was square root of x, that would not be fine. Square root of 2 is simply a number. 1.41 or something like that. Square root of 2 is okay. You have x to the fourth. That's what you're looking for. That's okay. Minus 12. Still good. Here's a problem. You have x squared, but then you have x to the negative 1. So that negative 1 is that fraction that I was talking about earlier. So that is not a polynomial function. And then over here, you have x squared, then you have 3 to the x power. So that's actually this part right here. That means that's an exponential. It's not a polynomial either, polynomial function either. So that is also both C and D, and you can see their explanations down here. C and D are not polynomial functions. Okay, so what I wanted you guys to do now was you can pause the video or you can watch the rest. It doesn't really matter, but what you're going to end up doing eventually is do number 3, number 5, and number 7. And see if these are polynomial functions or not. Check all your answers in the back of the book. Now on to the next part. Oh man, this is the easy stuff right here. I hope you guys can all do this. It's just saying evaluate this polynomial function when x equals 3. So it's just saying to find the value of the function when x is 3. So notice all you're doing at this point. I'm going to zoom in real quick. All you're doing is, for every single x on the polynomial function, you're plugging in 3. So you have 2 times 3 to the fourth, 3 squared. You have 5 times 3 minus 7. So they just plug in 3 for all the x's, or they substituted 3 in for all the x's, and then they evaluate the function. Now, so that's the answer. That's the final answer, 98. I don't know if you guys know this, just simple order of operations, so I'm going to say it before I continue on. If you're plugging in or substituting 3 in for your x, make sure you do that 3 to the fourth power first, and then multiply by 2, or 3 to the second power, then multiply by negative 8. That's important, okay? Because if you did negative 8 times 3, that's going to be negative 24, and then you square it, you're going to get a positive number out. But if you did 3 squared, that's 9, then multiply it by negative 8, you're going to get a negative number out. Okay, so it does make a big difference. So you square first, then you multiply. Square, then multiply. If you had a squared there, then you would do that, okay? But multiply by 5, subtract 7. I think I said squared a second ago. That's to the fourth power, so sorry about that. Okay, again, I would pause the video, and I would come over here to numbers 11, 13, and 15, and I would go ahead and work through those. It's just evaluating the function. 15 is a fraction, so that could get a little nasty. You might need a calculator to help you work through that. But it's pretty straightforward, guys. Just take whatever whatever value they're asking you to evaluate at, for example, x equals negative 12, and substitute that into every single x value. And if you wanted to really play it safe, I would put a parentheses around it. So for example, like this, negative, and then you have negative 12 to the third, plus 3 negative 12 squared, plus 5 negative 12, plus 1. And if you typed it into your calculator just like that, it would be fine. It would get you the right answer. And that's probably how I'd do it. Every single place you see an x at, I would put a parenthesis and insert that negative 12, or insert whatever x is. Maybe it's 8, negative 7. Maybe it's 1/2 or negative 1/3. That's how I would do it. Okay. Next part, We're talking about end behavior. So I'm going to see if I can zoom back out real quick. Okay, end behavior. Now, this could be a very easy concept. I don't want you guys to overthink it, and I'm going to explain it based on what you already know about quadratics, maybe. So remember, another name for quadratic is a polynomial even function. So this is x squared. And what you'll see happening when something is an even exponent, and what I mean by polynomial even is it has an even exponent. That looks awful. Give me a second. Okay. So when it's polynomial even, it's going to have an even exponent. So another example of a polynomial even would be x to the 4th, x to the 6th, x to the 8th, x to the 44th. Anything with an even number polynomial. All right? So what it is now is if it's a polynomial even, then on your graph, the end behavior, the end of this thing, as it goes to positive and negative infinity, is going to be going in the same direction. Now, if it's a polynomial odd, like y equals x to the 3rd, maybe x to the 5th, x to the 7th, x to the 9th, something like that, then instead of ending, remember end behavior, instead of ending in the same direction, both of these are pointing up, as you can see from the polynomial even, these are going to end in opposite directions. So if it's a polynomial odd, it looks like this. Looks something like that, okay? So, and that's just the general idea. Now, here's the something that's kind of neat. If I take, let's say, this x to the 3rd, so this is x to the 3rd. If I do y equals negative x to the 3rd, then we know that it just reflects over the x-axis. So it looks something like that. That would be negative x to the 3rd. So it reflects this axis right here. Okay. Let's say y equals negative x squared. Same idea. Reflects the x-axis. Looks like that. Okay, so that's the first idea. Now the second idea, so that's with squareds. They both end up pointing the same direction, except if it's negative, it points down. If it's positive, it points up. Cubes or odds, polynomial odds, they point in different directions. So if it's positive, as x goes positive, y is also positive. And as x goes negative, y is also negative. But if it's negated, then as x goes positive, you can see y is going negative. And as x goes negative, y is going positive. So you just flip it in that case if it's negative. Another really interesting thing to note is, let's go some polynomial evens again. So if it is y equals x to the 6th power, this is very interesting. That means it's positive. It's going to be, ultimately, the end behavior is going to be facing up this way and facing up that way, like that. That's going to be the end behavior. But there's a lot of stuff that's going on in between, okay? So if it's x to the 6th power, it actually is going to have 5 different turns in here, okay? So what I mean by that is, like, it's coming down, turns once, twice, 3 times, 4 times, 5 times, and then it's going to come back up and end up going in that direction. So it's always, however many turns it is always 1 less than your power. So that's something that's very interesting. So for example, what would that look like for a polynomial odd? All right, so if I have y equals x to the, let's say, 7th power, that means it's going to be turning 6 times before it heads back down. So here's my graph. It's going to be coming from the top right and ending going bottom left, like that. Now, what it does in between might be kind of crazy. So it goes turn once, twice, 3 times, 4 times, 5 times, 6 times. Now, this is all just an idea, guys. These are not the exact curves at all, okay? They're not the exact curves, but that's how many times it bends in between, okay? So that is a pretty interesting concept. So let's go back to this. x squared function, right? An x squared function bends one time before heading back up. So here it is, coming down, bends once, goes back up. If it's a negative x squared function, it still bends once, it's just facing down. So it goes up, bends once, facing down. X cubed function bends twice. So it's coming down, bend here, bend there. Two different bends. Negative x cubed, coming down, bends twice. Once, twice. Interesting concept. All right, so now I would again pause the video and I would try to discuss now what it's talking about right here. Let me zoom out real quick. What's talking about right here in numbers 17, 18, 19, and 20 on page 214 is in behavior. It's just saying, okay, what we want you to look at, and I'm talking in the, like the book now, but this is what it's trying to get at. What we want you to look at is, we want you to look at this first term right here. Now, remember, you want to place all these in descending order. So 11 does not matter in this case, and actually x to the fourth doesn't even matter. The ones that matter are the ones with the biggest exponents on them. So this one matters, this one matters, x to the eighth is the biggest here, and negative x to the fifth is the biggest there. So what this is saying, it wants you to notice, is that it's polynomial even, so it's facing up like this, or I mean it's ending in the same direction, except because it has a negative coefficient, it's facing down. So it's going to come up, it's going to bend actually 3 times, then it's going to come back down, something like that. And that's what it wants you to tell it. So describe the end behavior of the function. You could say maybe as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. This one right here, it's positive 7 for the coefficient, but it's a polynomial odd. That means it's facing up this way, and then it does a lot of moves around here, then it ends up going down in the end. So it goes from up over here to down. So as x goes to negative infinity, your function goes to negative infinity. And as x goes to positive infinity, your function goes to positive infinity. That's how you describe end behavior in this one. Number 19, and I realize I'm just going to go through all these answers with you guys, so I want you to pause the video after this and make sure you understand what I'm talking about. X to the eighth, so that's polynomial even. And then it has a coefficient of positive 12. That means it's facing up. So it's actually coming down from the left like this, and then it's bending 7 times. 1, 2, 3, 4, 5, 6, 7. And it's going back up. So as x goes to positive infinity, as x moves to the right, and what I'm saying is this right here. As x goes to the right, y is going also up. So as x goes to positive infinity, y is going to positive infinity. As x goes to negative infinity, y is going to positive infinity. And then lastly, you have a negative coefficient here, and then you have an odd. So it's a polynomial odd with a negative coefficient. So instead of coming down from the right, you're actually coming down from the left. So it flips over the x-axis, and it's going to end going down to the right. And it's going to have 4 different turns in between. So the reason it's coming down from the left like this, then ending going down to the right, is because it's negated. So 4 different turns. So 1, 2, 3, 4, something like that. So in behavior, as x goes to negative infinity, the y goes to positive infinity. As x goes to positive infinity, y goes to negative infinity. So that would do it for in behavior. The last little bit right here, guys, if you look over to the page over right next to you, on page 215, you're looking at numbers 25 through 28. I'm not going to make you do a ton of these, but I will make you do probably, let's go with 4. So 25 through 30. And so what it tells you is, knowing that this thing bends, it's just, give a general graph. You could always check your graph on the calculator, but knowing that this thing bends 3 times, it's a polynomial even, it's negated, so it's facing down. So a general idea would be like this. It's facing down, it's bending 1, 2, 3 times. So they're both going down like that. Make a table. So what it's going to want you to do is to make a table. And you can even see example 4 if you want, just to verify and get better instructions. Make a table, x, y, and it's going to say plug in the numbers 0, -1, -2, 1, 2. So it's going to say plug these numbers in for your x terms right here and get your y's out. So plug these numbers in, get the following y's. I'll just do it real quick. We've got -2 to the 4th power. -2 to the 4th power is 16, and that's a minus 16. So 3 minus 16 is going to be -13. -1 to the 4th power is 1, and then it's a minus 1, so it's 3 minus 1 is 2. 0 to the 4th power is 0. 3 minus 0 is 3. And again, it repeats itself now. 2 and -13. And it's going to want you to graph that. So I want you to do number 25, 27, 29, and 30. Don't make, 29 and 31. Don't worry about making a perfect graph. Do not make a perfect graph. So notice it goes from -2 and -13. It's going to take a lot of space if you're going to make a perfect graph. I do want it to be close, but for example, if you were going to graph it something like this and just have 1, 2. So x is -2 and then y is -13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Put a dot there. Notice it's not perfect, it's estimated, but it's a little more accurate than a sketch, just a straight up sketch. All right, guys. So go ahead and work on that tonight. So that's your homework. Again, it's going to be the odds. Zoom out one more time. It's going to be all the odds pretty much. It's going to be 3, 5, 7, 11, 13, 15, 17. I want you to look at 17, 18, 19, 20 since I did them all in the video. And then 25, 27, 29, and 31. And that should do it.